Section: Introduction. In this section, we introduce transformer-based large language models, like Llama and GPT, which generate responses by predicting the next token in a sequence. These models create tokens one after another, but this method can fall short for complex tasks. Recent research has looked into enhancing these models by adding auxiliary tokens to the input sequence, which can either have clear meanings, like chain of thought, or act as abstract placeholders. By allowing the model to process these additional tokens before generating the next ones, we can improve the quality of the outputs. We differentiate between interpretable methods, which use tokens with clear meanings, and non-interpretable methods, which insert special tokens that may not have explicit meanings. Examples of non-interpretable tokens include pause and filler tokens, which can enhance model performance beyond the limits of natural language. However, these tokens are usually placed at fixed positions, such as the start or end of a query, which can reduce their effectiveness, especially in longer sequences or those that differ from the training data. To address these limitations, we propose a straightforward yet effective method to augment any decoder-only transformer with latent tokens. These dummy tokens do not correspond to natural language and can be flexibly applied during inference, enhancing computation before predicting any output token. We detail the design of these latent tokens, including how they are used during inference and training, and ensure they are broadly applicable without requiring extensive retraining of the transformer. Our approach shows consistent improvements in performance across various benchmark tasks. However, we still need to understand which tasks benefit most from these latent tokens and why they are effective. Therefore, we explore several hypotheses regarding their utility, such as aiding in long and consistent generation, assisting information retrieval, and improving adherence to instructions in longer out-of-distribution sequences. For each hypothesis, we create synthetic tasks to evaluate our method against existing approaches, and the performance improvements, especially in out-of-distribution scenarios, suggest the advantages and potential mechanisms of the latent tokens. Section Summary. In this section, we introduce a method to enhance transformer-based large language models by incorporating latent tokens during sequence generation, which allows for additional computations and improves performance on complex tasks. We also explore the design and application of these tokens, highlighting their potential benefits in long and out-of-distribution sequences. Section: Latent Tokens, a Unified Methodology. In this section, we introduce our method for integrating latent tokens into the decoder-only transformer, as illustrated in the accompanying figure. These latent tokens provide additional computational support to help the model generate output tokens through the attention mechanism, but they are not meant to produce extra outputs with clear verbal meanings. We aim to achieve several key properties for these latent tokens. 1. General applicability. Our approach should work with any decoder-only transformer and be suitable for various tasks, not just specific ones. 2. Latent computation. The latent tokens assist in generating output tokens without necessarily creating additional interpretable sequences. 3. Minimal disturbance. We strive to minimize any negative impact on the original distribution of verbal tokens when adding latent tokens to a pre-trained transformer. We introduce a set of latent tokens, labeled as U1 through which are new tokens not found in the original vocabulary. Each latent token UI corresponds to a learnable vector in a specific dimensional space. Next, we detail our method's design, including the inference and training processes, as well as the choices made regarding the latent tokens. During inference, we incorporate latent tokens into both the query and the generated response to enhance computation. We assume that latent tokens have been added to the query sequence at appropriate positions, following the same procedure used during optimization. Based on this modified query, the transformer generates the first response token. Importantly, the output remains within the original vocabulary, as we do not expect the model to produce latent tokens in the output. The inclusion of latent tokens also aids in predicting subsequent tokens during the generation process. To facilitate this, we assign position IDs to both the generated verbal tokens and the latent tokens, ensuring the transformer accurately understands their relative positions. For the position encoding of latent tokens, we maintain the position information of the input tokens, ensuring that the addition of latent tokens does not disrupt this information. We propose using the same position encoding for the latent tokens as for the following verbal tokens. Specifically, we keep the position IDs of all verbal tokens unchanged and assign the position ID for the latent tokens right before the verbal token. This design allows the model to effectively capture the positional information of both types of tokens, which is essential for understanding the input sequence. Our approach is compatible with various positional encoding schemes, from the original absolute position embedding to newer methods. To optimize the latent tokens, we preprocess the training data by inserting them into the input sequences. We can place these tokens at any position within the sequences. For instance, if we use a group of M latent tokens between two input tokens street and saint plus 1, the model learns to predict the output tokens based on the augmented input sequence. In our current work, this optimization occurs during the fine-tuning stage of a pre-trained transformer model, while the pre-training stage remains unchanged. We focus on optimizing the latent tokens while keeping the pre-trained model parameters fixed, offering a more efficient way to enable latent computation compared to existing methods. Section Summary. In this section, we introduce our methodology for integrating latent tokens into decoder-only transformers to enhance output generation without producing additional interpretable sequences. We ensure that these tokens are applicable across various tasks, minimize disruption to the original model, and maintain the integrity of positional information during inference and optimization processes. Section: Loss Function Design. In this section, we discuss the design of our loss function. We expect the latent tokens to help the context sequence in predicting the next token. The loss is calculated using specific token indices, focusing only on the predictions of verbal tokens while ignoring those of the latent tokens. Our goal is to minimize the loss related to verbal token predictions. Notably, our method is versatile and can be applied to any decoder-only transformer model. It allows for efficient fine-tuning of latent tokens without needing to retrain the entire model. Additionally, we can utilize existing training and inference infrastructure with minimal added complexity. Next, we outline our design choices for incorporating latent tokens into the sequence. We can insert any number of latent tokens at various positions, either fixed or variable across different inputs. A simple approach is to add a set number of latent tokens at regular intervals, such as after a certain number of verbal tokens. We can also place latent tokens based on specific markers like commas or periods. We also introduce a function specialization option, where latent tokens can have different roles based on their positions or the verbal tokens that follow them. For instance, we can use different groups of latent tokens at the start, middle, or end of a query. This specialization helps avoid conflicting learning objectives, enhancing model performance with fewer trainable parameters. We compare our method to related approaches. For example, if we only add latent tokens at the start of the query, it resembles prompt tuning. However, our approach is more flexible, allowing for complex tasks by placing latent tokens in various positions. We also discuss pause and filler tokens, noting that while they serve specific functions, our latent tokens are more broadly applicable and require less fine-tuning. Our strategies for inserting latent tokens align with the autoregressive nature of LLM decoding, where the decision to insert a token depends on the preceding context. We find that simple strategies, like inserting tokens at specific verbal markers or periodically, yield satisfactory results in both synthetic and benchmark tasks. Finally, we explore the potential benefits of latent tokens in downstream tasks. We propose 3 hypotheses and plan to test them through carefully designed synthetic tasks, with detailed experimental setups available in the appendix. Our first hypothesis suggests that repeated insertion of latent tokens during generation can help the model maintain long and consistent outputs by reminding it of learned information. Section Summary. In this section, we propose a loss function design that utilizes latent tokens to enhance the prediction of verbal tokens in a decoder-only transformer model, allowing for parameter-efficient fine-tuning without retraining the entire model. We also explore various strategies for inserting these latent tokens, including their specialization for different functions based on their positions, which improves model performance while maintaining alignment with the autoregressive nature of the decoding process. Section: Setup. In this section, we design a task called generation to test our hypothesis. The model is required to generate a sequence of responses based on a specific rule for as long as possible. This involves creating equations from a rule learned during training. We define an operation that takes 4 digits as inputs and produces 2 results. The first result is the absolute value of the first digit plus the third digit, taken modulo 9, and the second result is the absolute value of the second digit minus the fourth digit, also taken modulo 9. The equations are structured in a way that combines these results and is followed by a comma, totaling 6 tokens when processed by the llama-3.2-1b tokenizer. Next, we replace parts of the equation with the results from our operation. Each sample starts with a beginning token and includes 5 equations. The model is expected to generate as many equations as possible within a set token limit, but it must learn this rule from the training examples, as it is not explicitly provided. The responses vary in length from 1 to 10 equations, without an ending token. We implement different versions of our method and track how many correct equations are generated, comparing them to baseline methods. The baselines involve adding latent tokens at the start or end of the query, while our method inserts latent tokens before each comma. We evaluate these methods in both in-distribution cases, where the samples match the training data, and out-of-distribution cases, where the model must generate more equations than seen in training. Our results show that our methods, _1 and _2, outperform all baseline methods with the same number of trainable parameters. The performance gap widens in out-of-distribution cases, with our method achieving a 23% relative improvement over the best baseline in extreme scenarios. We believe that inserting latent tokens before each comma helps the model segment the equations into manageable parts, improving coherence and structure in longer responses. In contrast, adding tokens at the start or end provides less context, limiting adaptability in out-of-distribution situations. Thus, the _m method enhances the model's ability to generalize and accurately handle a wider range of equations. To further explore the impact of latent tokens, we visualize the attention maps for _2. We notice a repeating pattern every 8 tokens, consisting of 6 verbal tokens and 2 latent tokens, which becomes more pronounced in the last layer. This suggests that the latent tokens play a crucial role in guiding the generation of subsequent equations. For our second hypothesis, we propose that latent tokens can assist the model in retrieving relevant information from the input sequence. To test this, we create a task called summation, where the model must extract relevant information and provide the correct answer. Each input sequence includes a list of variables with integer values ranging from 10 to 30. The query ends with a question asking for the sum of 2 randomly selected variables from this list. While calculating the sum is straightforward, the challenge lies in accurately extracting the necessary information from the sequence. We set the number of variables in each training sample to be between 5 and 15, while evaluations can include test samples with more variables, representing out-of-distribution scenarios. Section Summary. In this section, we design 2 tasks to test our hypotheses. The first task, generation, involves generating equations based on a learned rule, where we find that inserting latent tokens before commas significantly improves the model's ability to generate coherent responses, especially in out-of-distribution scenarios. The second task, summation, focuses on extracting relevant information from a list of variables to compute sums, highlighting the challenge of information retrieval despite the simplicity of the arithmetic operation. Section: Results. In this section, we vary the number of variables and assess the performance of different methods, including several versions of our proposed method, as shown in the figure. Our method, referred to as _2, significantly outperforms the tuning method, start_2, particularly in out-of-distribution OOD tests with a larger number of variables. We notice that as the number of variables increases, the performance of all methods tends to decline. However, our method still performs reasonably well even when the number of variables exceeds 10 times what was used during training. We also evaluate the impact of periodically inserting latent tokens, represented by K_M, which means M latent tokens for every K verbal tokens. This periodic approach, labeled 8_2, also shows promising results, achieving a 127% relative improvement over the best baseline, start_2, in an extreme OOD scenario. We conclude that latent tokens assist in retrieving relevant information from input sequences, possibly acting as anchors to help locate necessary information for answering questions, although further investigation is needed to confirm this idea. Next, we hypothesize that using latent tokens during autoregressive generation can enhance the model's ability to follow instructions, especially for generating longer sequences. To test this, we design an instruction-following task called repetition, where models are instructed to repeat a given equation a specified number of times. Each sample starts with a base equation of the form a plus b equals c, where a and b are random integers between 1 and 100, and c is their sum. The query includes an instruction to repeat the equation n times, followed by the equation repeated s_1 times, with s_1 randomly chosen from 1 to 5. The model must then continue the same equation s_2 more times, where s_2 is the total n minus s_1, ranging from 1 to 10. During training, we only use samples where s_2 is between 1 and 5, while s_2 greater than 5 serves as OOD evaluation. Our preliminary studies reveal that the base model, llama-3.2-1b, struggles to complete this task without fine-tuning. Unlike the generation task, the model receives an instruction but must remember the current generation status and adhere strictly to the repetition count. To address this, we introduce latent tokens with function specialization, called comma_1, WFS, where a latent token is added at the start of the query, and another is inserted before each comma. From our experimental results, we observe a significant drop in performance in OOD scenarios compared to the 100% accuracy in the in-distribution ID setting. Upon reviewing the incorrect samples, we find that all errors stem from miscounting the equations, highlighting the challenge of achieving the correct count when it was not seen during training. In contrast, our method, comma_1, WFS, achieves much higher accuracy than all baselines, with a 220% relative improvement over the best baseline in an extreme OOD setup. This demonstrates the effectiveness of function specialization in adapting latent tokens for various functions. Specifically, one latent token may memorize the instruction while others focus on previous latent tokens to access the current status. In the appendix, we provide preliminary evidence that latent tokens may influence the ending of sequence generation by attending to the starting latent token and instruction tokens. In the extended comparisons, we address whether the performance gain from latent tokens is simply due to the increased computation from extra tokens. To investigate this, we compare our method with baselines that have the same average number of tokens. We set the number of added tokens in the baselines to 23, 20, and 7 for the generation, summation, and repetition tasks, respectively, to match the average input sequence length used during training. Our method significantly outperforms the baselines in OOD scenarios, demonstrating its generalization ability. Additionally, we observe that increasing the number of learnable tokens in the baseline methods does not consistently lead to improved performance, a trend noted in existing literature. Overall, our results suggest that the advantages of our method arise not only from increased computation but also from the more effective design of latent tokens. Section Summary. In this section, we demonstrate that our proposed method, comma_2, significantly outperforms traditional tuning methods, especially in out-of-distribution OOD tests with many variables, while still maintaining reasonable performance even with a substantial increase in variables. We also find that incorporating latent tokens enhances instruction adherence in longer sequences, achieving notable improvements in accuracy during OOD evaluations, indicating that the design of latent tokens plays a crucial role in their effectiveness. Section: Related Works. In this section, we discuss related works on learnable special tokens. We have seen that adding learnable tokens to transformers has been explored for various reasons, such as remembering previous sequences, enabling adaptive computation, compressing data, and reducing artifacts in vision transformers. To enhance reasoning skills, some researchers have suggested inserting pause tokens within or at the end of queries. Others have used filler tokens, referred to as dots, to replace the chain of thought process, showing improved performance in specific tasks compared to cases without this approach. However, these studies often struggle to achieve optimal results by directly fine-tuning these special tokens, which leads us to seek a more effective method for introducing latent computation. Additionally, some work trains large language models, LLMs, to create a planning token at the beginning of each reasoning step to guide better reasoning. Most of these studies focus on tasks with clear reasoning steps, which limits their applicability to other tasks. We also note that tuning can be seen as a prior effort to add special tokens to input queries, which aligns with our proposed method. In broader related works, we observe a growing number of studies showing that incorporating intermediate computation steps can improve LLM performance across various applications. For instance, many studies, including chain-of-thought approaches, encourage LLMs to generate intermediate steps explicitly to boost reasoning abilities. However, this confines LLMs to reasoning within natural language space, which can lead to limited performance in some scenarios. Another research direction suggests using hidden computations to guide model outputs, although these hidden computations may not have clear meanings in natural language. While these methods enhance reasoning capabilities, they often require extensive training of the entire transformer model, making them challenging to adapt to different tasks.